Hello, good morning, everyone, and thanks for attending this Predictive Maintenance for Optimized Manufacturing Solution in Industry 4.0. This is an event supported by the DFA aimed at predictive maintenance for Industry 4.0, organized by some of the most important current European agents, which are also part of the 4C clusters. To present the best solution for predictive maintenance based on the most advanced technology, such as IoT, digital twin, proactive computing, virtual augmented reality, and linked data. Before leaving the floor to Sotiris Makris and the 4C cluster, let me briefly present you the Digital Factory Alliance. The Digital Factory Alliance is a community for digital integration and data-driven transformation. The idea of this alliance started when we observed together with other agents, among them the World Economic Forum and their platform, Advanced Manufacturing and Production, that most of the new technologies languish in pilot purgatory. This means they are tested. It is shown that they work, but there are some difficulties when it's time to reach the market. What we would like to achieve with the Digital Factory Alliance is to leverage on the digital assets like digital integration and data-driven intelligence to address the most important challenges of the factory, to get resilience, sustainability, and efficiencies that provide value. These two elements put together will give what we call the smart rapid response. It means the tool for the manufacturing companies to react to each type of event that was not foreseen. So the DFA mission is to build an international trusted community for digital factory stakeholders to foster knowledge sharing and industrial collaboration in digital integration and data-driven intelligence for smart rapid response in manufacturing. The Digital Factory Alliance was established in April 2021. Here you have a picture of the signing ceremony. Association, Atos, and engineering. Beyond the founding members, we have already several members from different countries of Europe and a network of a lighthouse factory. You can see the name here in these pictures. And among our collaborators, we have the already mentioned World Economic Forum. The benefits of the Digital Factory Alliance for our members are the opportunity to participate in our rapid response initiative, steer your data-driven intelligence strategy, and improve your resiliency and excellence in zero-waste manufacturing. Gain visibility and connect your smart rapid response product, achievement, and solution globally. Qualify your digital rapid response manufacturing capabilities and get ready to connect and collaborate with peers. Access timely to unique insight and selective reports on the most recent trend, the smart rapid response technology manufacturing, and organize and participate in our DFA events. Among our rapid response flagship initiative, we have a different level of action. At the factory level, we would like to establish open, integrated, and high-performance optimization models for autonomous adaptation to manufacturing disruption. At ecosystem level, inside the Manufacturing Global Response Initiative, we would like to establish monitoring, preparedness, and production repurposing networks for rapid response against value chain disruption. and to provide value, our Lighthouse Digital Factory initiative to improve global visibility of rapid response digital manufacturing solution to reduce the stay in pilot purgatory. And our next initiative, we would like to write it with you, with your collaboration, with your ideas and support. If you are interested to join, you can register in the website of the Digital Factory Alliance.eu in the tab Join Us. And before closing, I would like to remind you the next event of the Digital Factory Alliance, the Digital Tech Talk, European Zero Defect Manufacturing, organized by the 4ZDM cluster with the support of the DFA. You still can register. It will be on 8th of July in 2 days at 9 o'clock in the morning. And also the DFA ebook that will be coming soon during the summer. Here you have our contacts detail. But now, let me give the floor to Sotiris Makris, Senior Research Scientist in a Laboratory for Manufacturing Systems and Automation located in Patras. Sotiris has a large experience in the participation and managing of several European projects, and also a part of the 4C cluster. So, good morning and welcome, Sotiris. I leave the stage to you for this interesting event. Thank you.
Good morning, Carmen. Good morning to all the attendees, and I would like to thank beforehand my colleagues and speakers that will follow on to share with the audience our experiences through the 4C cluster. We appreciate the support and the collaboration with the Digital Factory Alliance, and also the opportunity to have this first digital talk, and we find it a rather interesting experience. We are very glad, and I will start sharing with you some material to share our effort and our work over the past years on the 4C cluster. And this is actually a pleasure for me to share these experiences and lessons learned, and also conclusions from this inspiring group work that took place in the context of the 4C cluster. In this course, we had the opportunity to meet with high-quality European research groups all around Europe, as well as to confront with strengths and weaknesses of European industry, and also investigate paths from the future. So I will move on to tell you a little bit more about this cluster. This cluster is a joint effort of 6 innovative projects funded within the European Commission call from the Factories of the Future program. We started in 2007. The vision of this cluster is to create a sustainable predictive maintenance set of solutions for the factory of the future. And the actual mission on how to do that is to create a roadmap for predictive maintenance based on the experiences we gained in these projects. There are 6 projects, namely Prophecy programs, Precom, Serena, Uptime, and ZBreak, and around 80 organizations from Europe participated in this initiative. How we work together, we have started with an open-minded culture and approach. We try to set down technically our objectives. We put together a number of so-called activity areas, and you can see the activity areas we prioritized. So we started jointly working on analysis of technology in the market and the pipeline. And then from that, we were developing a common concept, as far as common as possible, a concept on predictive maintenance for the factory of the future. We have been analyzing and debating trend setting for the future factory. We explored and discussed on new models for sustainable factories through efficient predictive maintenance. Also, we elaborated through the idea of analyzing skill requirements, what kind of skills should we identify for running such factories involving predictive maintenance. And we tried over the time and over the years to build our community. Of course, apparently, a core item in all of our projects is data integration, machinery connectivity, modularity, pre-processing of the data at different nodes and stages of the network, cloud, fog, edge architectures, skills development, and so on and so forth. We investigated different methods of artificial intelligence that have emerged over the years, and we try to put them into practical use. And we will be glad today in the following presentations to go in more detail, sharing what we have done together with our industrial partners. Then this work has been structured, has been guided on the one hand from the activity areas, but on the other hand, we thought to structure it and have an output that we decided to have, to call it a white paper. So we created this roadmap in the form of a white paper. And the actual content we investigate is this new paradigm of predictive maintenance, how SMEs or larger industry would adapt and adopt these solutions. We have been investigating competencies and roles and defining the skill set required for running such technology. We have been thinking and trying to contribute to future research agenda. Also, we thought on contributing towards the development agenda of industrial and technology companies, and overall to enhance the European industry innovation capacity as a whole. In the bottom of the slide, we are sharing the link to the web page of the actual cluster, where the actual work, the white paper is actually available. And as we move on, we will discuss during the next couple of hours the actual content of the white paper with the help of the items that I show here. And this is actually the agenda for the next points. So before we go into discussing deeply the white paper overview and the actual chapters and the content that we have developed, we will have an introduction and some feedback from our honored guest, Chris de Camper from EFRA, the European Factories of the Future Research Association, to put in context of the EFRA, the predictive maintenance activities. And then we will go a bit deeper. We will have Kosmas Alexopoulos from LMS, my colleague, to introduce the overview of the white paper. And then we will have more specific presentations on different chapters. Karl Kribernik from BIBA will talk us about the vision of PDM in manufacturing. Michele Surikor from PDI will talk us about key enablers in PDM. Nikos Nikolakis from LMS also will explain us when we will guide us through industrial use cases. Basim Al-Nazar from Precom project at Linnaeus University will take us through the journey of roadmap for industry practitioners. And two colleagues, Yves Geranon from Isadeus and Hugo Faria from Innova in Portugal, will talk us about how we explore the standards and standardization aspects. And finally, Ioannis Soldatos from Microsoft will tell us how we concluded with recommendations for future research. Each of the people is coming from a different project. Each project has been leading a chapter. So this is really shared work and community effort, and we are very glad to share with you today the outcome. So this is the list of our next speakers, as I already summarized. From my part, I will be chairing and the session and facilitating the discussion. Again, feel free to use the link of the cluster web page to access material, and you are very welcome to get in touch with us, and if we can help to clarify better different aspects, we will be very glad. So I'm very happy now to invite Dr. Chris de Camper from EFRA on stage and share with us his view. Chris, good morning and welcome to this event.
Thanks a lot, Sotiris, for this introduction. Thanks for the invitation. If all is well, and I will put it in presentation mode. You see my screen now. Right, so yeah, thanks for the invite. I will give you some introduction, putting this cluster of projects into perspective from maybe the past towards the future. EFRA, European Factories of the Future Research Association, is the partner to the European Commission, and still is the partner to the European Commission in the Factories of the Future program, and has now become very recently the partner to the European Commission for the Made in Europe partnership under the Horizon Europe program. So what we do is twofold, basically, essentially. We're consulting with stakeholders on the priorities and are discussing with the Commission how to integrate these priorities in the programs. And on the other side, we are looking into what's happening in the projects, what's the outcome of the projects, and valorizing as much as possible, disseminating project results and creating the community around all these projects. I'm here in this picture. I'm showing actually an update of the Factories of the Future roadmap that we did in 2016, looking forward in the three last call topics to Horizon 2020, and then making a stepstone towards Horizon Europe. And you see there that, well, in the middle, you see excellence very much in the picture there. And in the bottom, you see the notion of interoperable digital platforms. And I think also this cluster of projects is one of these projects that really feed into this evolution towards integrating digital solutions for the sake of quality. And of course, predictive maintenance is a very particular component in that. So very much we're really continuing in the flow. This project is from the 2017 call topic. So clearly also there we were continuing on the motion that was put in place already in the calls before. And hence, yeah, as Sotiris introduced, we have this cluster of projects on the novel design and predictive maintenance from 2017. But clearly, we are continuously building using these focused projects on, here in this case, on predictive maintenance and other projects that I will refer later, as in a common evolution. You can call it towards Industry 4.0. We can call it now the transition. There's many ways to call it, but definitely there's a lot of things happening. And one of the examples I wanted to give was, for instance, the quality project that was born actually a year later in the digital platform projects, where we see many stakeholders from both the digital side and the hardcore manufacturing side coping together to make sense of data and using this data for the sake of quality. So there's a cluster of projects also that was built along the context of digital platforms. And I believe that the results that the predictive maintenance for C cluster is developing is very relevant also to illustrate what you can do with the data very specifically. So I'm very grateful also to see the results of those projects. Now, very briefly, to put this in a wider perspective, EFRA has been stimulating via the Connected Factory CSA also the perspective from the pathway point of view. We are building the building blocks, we are developing the building blocks within the program to advance towards, you can call it advanced digitalized manufacturing, smart manufacturing along different levels within the factory, on value network level, and focusing also on the creation of this collaborative product services. And the service approach, I think, in the context of predictive maintenance is very important. We have more and more stakeholders being part of this ecosystem to provide services on top of the manufacturing capital equipment for the sake of quality and for the sake of productivity, hence the role of predictive maintenance. So here also in a very basic pathway where connectivity is a main aspect, we look into how the different levels of optimization can be reached, being offline or being real-time interaction on the systems. In a very basic way, we're looking at this, but of course the cases are quite in-depth And here I bring in a case from the BNCPPS project, which is an I4MS project that also illustrates very well the technological aspect and the data, the need for data connectivity in order to be able to provide services that enable a manufacturing equipment supplier become also a service provider to the equipment that is in the different factories all around the world and be able to connect to the systems to provide maintenance services. So there's a whole world of standardization. OPC-UA is mentioned there. I could mention industrial data space as well. So this is all becoming part of one big context where actually this predictive maintenance services also become an important aspect. I mentioned already the pointer to the collaborative product service factories, where actually within connected factories and from the point of view of EFRA, we would like to develop further the insight into how product service development in manufacturing is taking place and what building blocks you need to make that happen. And of course, connecting with your customer is an important aspect in this, and the technologies to enable that are, of course, very critical. From product lifecycle management systems, CRM systems, to the whole product data, industrial data space systems that we are now discussing more in detail. So many programs now are looking into data spaces. I think also here, that's where the predictive maintenance services come in. So there's many ways to look at predictive maintenance, how it fits from the technological point of view, from the data capturing point of view, from the data business point of view. Hence, we're also very much focusing on this development of data spaces. And the link with AI is also very much there, because the more data you have also for predictive maintenance, you would be capable to implementing AI for predictive maintenance. And we're not there yet, clearly. Predictive maintenance, the projects from the 4C cluster are paving the way to more insight into using this advanced AI, advanced data analytics technologies for the sake of predictive maintenance. So again, happy that we have these building blocks to progress further. I mentioned the data space pathway already, just mentioning that again, predictive maintenance as a goal is like straightforward. Many things around it make life maybe a bit more complicated if we have different stakeholders involved, like data sovereignty, data ownership, the whole security aspect of connecting to machines elsewhere, vulnerabilities that can be caused. Of course, there's the added value of being able to provide the maintenance. Of course, you have to look into the fact that the machine is still, of course, secure, and that connectivity, of course, is taking into account the security constraints. So there's many boundary conditions. Skills is another one, clearly, but there's many also technical boundary conditions that will have to be matched in order to make predictive maintenance roll out across the industry. This relates also to digital twins, to the fact to be able to know what's going to happen before it actually happens. That's what predictive maintenance is about. So then we come into the context of having this asset administration shell concept rolling out, being able to connect to the different services that are around, and hence the link with standardization is very obvious. So it's a quite broad context, and within Horizon Europe, definitely we're looking forward to develop these opportunities more. The call topics are really now published, so they're really there now, and I think there's a lot of focus now on using the opportunities. What I can say there is that the evolution is the twin transition. Clearly, the environmental sustainability aspect together with the quality aspect for predictive maintenance, we see that these aspects are being more and more coupled. So I think also there the link with sustainability is one that also from your perspective probably you will think about. Last but not least, I would like to invite you and certainly also all the 4C projects to promote their cases, and hence we have launched the Digital Transformation Cases Catalog to situate the cases along the pathways, particularly also around some particular enabling technologies, be it data connectors to achieve the interoperability, or security approaches, or AI approaches. So definitely we like to promote the cases so that the wider community really sees quite quickly what's the added value of the work that has been done, and then can jump more deeply into the technological aspects. So with this, I would like to conclude this brief introduction and intervention, and I'm looking forward to this webinar and the project results that you will present. Thank you very much.
Chris, thanks a lot for the participation and also putting things in context. Indeed, all the topics you mentioned, the data availability, AI approaches, different objectives, availability of machinery, lifetime extension, there are many things, and that this work from the cluster can contribute to the future. And thanks a lot for being with us and commenting with us your views.
A pleasure.
We will move on with the next one. So we will now start diving into the actual work and to the white paper content. The next speaker will be Dr. Kosmas Alexopoulos from LMS that will bring us through this journey of the white paper. Please, Kosmas.
Hello, thank you, Sotiris, for the introduction. In this presentation, we will have an overview on the white paper developed by the 4C cluster, and we will see some information on really on the development process itself. So a few let's say infographics and few information to be said regarding the development of the white paper. This was the collaborative work of several people coming from 6 projects, 6 Horizon 2020 projects that were working on the topic of predictive maintenance. In total, there were 9 editors involved in the preparation of the white paper. More or less 1 or 2 were assigned per each chapter to work upon it. But there were not only the editors, there were several contributors coming from the project. So we had something like 25 contributors that they provide input and to the paper. And this all this development lasted for approximately 20 months. So it was 20 months of very interesting and exciting collaborative work that resulted in our white paper, which is it has approximately 100 pages. So there is a lot of material in there, a lot of work being reported in 7 chapters and 2 annexes. And also I would like to focus that in the paper, in the white paper, we are presenting 18 industrial pilots that come out from the 6 Horizon projects. And also some information on the development of the white paper. More or less the work started already from 2019. There were discussions even before the very first, let's say, kickoff of this activity on the content and on the objective of the white paper. But in any case, the outline was delivered in December 2019. And then throughout 2020, the main part of the work took place. The projects were the different editors and the projects were delivering work to be included in the white paper. Of course, there were several iterations and review phases and for the different chapters, and also it was an ongoing work as the project were also progressing with their actual work. So in many cases, the content had to be updated. In any case, we managed to have a first compiled version in October 2020. And in February of 2021, the first draft version with all chapters but standardization that was added in the late months of the work were already in a draft phase. And end of April we have the full draft, so we can proceed with editorial changes, proofreading, and all this. And now we're very happy to publish it in the 4C cluster portal. Now, a few words regarding the structure and the overview of the white paper. The purpose of this white paper is to share the 4C cluster understanding of future condition monitoring and predictive maintenance approaches for the factories of tomorrow, and also to provide the recommendations on how to bring this vision into industrial practice. And now, if we you see here the structure of the chapters. In chapter 2, the vision for predictive maintenance manufacturing has been presented, and this describes, it tries to compile the 4C cluster's vision on future predictive maintenance tools. Then in chapter 3, we report the key enabling technologies that can be utilized to implement the vision. And this chapter basically presents the key technologies used by the 4C cluster projects. Then we move on to chapter 4, which is the industrial pilots. And in there, we provide insight and lessons learned by applying the technology described in previous chapters on several 4C cluster projects in several industrial pilots. The challenges, the solutions, and the impact on the cases is being discussed as well. Then chapter number 5 discusses on the standardization aspect, which is an important topic when it comes to predictive maintenance, and what are the standards in data being used, technology being used, and also business processes applied in order to support maintenance and predictive maintenance activities. And then we move on chapter 6, which is provides a list of recommendations or analyzes the recommendations for industry practitioners, so as to help them, to guide them when they are into some predictive maintenance project in their industry. And last, chapter 7 provides recommendations for future research directions and policy makers. So we try to cover both industry and research and policy makers with the results of this work. As said, the white paper is there available for download from the 4C cluster. It's already on public domain, and we hope you read it. You find it you find interesting material and interesting information in there. But in any case, we will have the chance to discuss all of it in the next presentations, in the next session that focuses on and presents its chapter individually. That's all from my side. Now I think we can move on to the main part of the event, which is the presentation of the white paper.
Great, Cosmas. Thanks a lot. Thanks a lot for going us deeper into the actual content. The next colleague will be Karl Hribernik from BIBA, that will try to introduce to us the vision that we have been exploring for predictive maintenance in manufacturing. I would like from now on just to go on with the schedule, just to remind that we are aiming for about 15 minutes presentation from all of us. Thanks a lot to everyone for the preparation, and please, Karl, the floor is yours.
Thank you very much. I'm trying to share my screen. There we go. So, yes, thank you very much for the introduction, Sotiris and Cosmas, and also Chris. And thank you, everyone, for joining us here at this 4C Cluster Digital Tech Talk today. And we're very happy to be able to present the results of the roadmap, which Cosmas quite rightly highlighted as been a lot of work over the last years, and I think we're all quite proud to have developed it. So the topic of my talk is a vision for PDM and manufacturing, and I think it will be a little bit of an introduction or a preparation for the presentations that are coming. So we'll look at the background of predictive maintenance based in current trends in maintenance. We'll look at drivers of the trend towards predictive maintenance. So what is the causes and the reasons that predictive maintenance are coming up, and the drivers. We'll look at barriers to why predictive maintenance hasn't been adopted very widespreadly so far, and then we'll go into the different phases of predictive maintenance, starting with data acquisition. So looking at how digital transformation strategies need to be defined for predictive maintenance. Then, of course, the next step is detection, so condition detection of assets, and then prediction, looking into the future to see how these assets will perform, which are the cornerstones of predictive maintenance, and then two phases in one, so the decision taking and acting upon predictions in predictive maintenance on all levels. Then underlying everything, as we have already seen, standardization and interoperability of predictive maintenance systems. I will show quite briefly the 4C PDM system reference architecture, and then give some conclusions and an outlook. So starting with the current trends in maintenance, of course, maintenance impacts directly on key issues that are present in all industries. All industries are obviously interested in minimizing their costs. Maintenance can help by saving labor, repair, parts, and tools costs, of course. Industry wants to maximize reliability and production efficiency. Maintenance can help by, of course, decreasing downtime of assets and production lines. Industry needs to look towards having a low environmental impact these days. Maintenance, especially predictive maintenance, is very helpful in increasing the remaining useful time life of assets, and thus contributing to sustainability. Safety is another key issue, and of course, if your assets are in good condition, then you will avoid accidents, and that's another plus point for maintenance. Maintenance is obviously then a key operation function of manufacturing enterprises, and there are different strategies conventionally how it has been realized. So either you have a dedicated in-house maintenance team, or you partially or fully outsource your maintenance activities. Over the last decades, the maintenance market has matured, and its growth has kind of capped around 2010. Since then, expertise and technical know-how are no longer really unique selling points, and improvements have been hard to squeeze out of the margins. So new pathways and strategies are required, and predictive maintenance is one of those pathways. Up in the top right, you can see the different paradigms of maintenance, starting at reactive or curative, corrective maintenance, so fix something when it's broken, which isn't so good, through to condition-based maintenance, where you're able to use data collected to understand how an asset is, and then maintain it when it's needed, and predictive and prescriptive maintenance, which we're talking about today, where you actually look into the future of an asset's condition based on data and analytics, and are able to then fix something before it breaks. Products and assets these days are becoming more and more complex, and there's a higher emphasis being placed on quality and reliability of both the production assets and the products. So the cost effectiveness of the time-based preventative maintenance or condition-based maintenance is decreasing. The predictive maintenance that we're talking about today is becoming a more attractive proposition because of that, and the foundations required for this kind of a more proactive maintenance strategy are already in place. So we're looking at getting data about assets which can be analyzed. Costs of sensors and PLCs are steadily falling. They're quite readily available in mature technology these days. appropriate network and communication technology is on the market or emerging, so it's no longer so complex to network your assets. And if we're looking at 5G, then it will become quite easy to network your assets and get the data out of them. Robust, reliable, and more affordable IoT and cloud solutions are available, and big data analytics and artificial intelligence solutions are on the market that can do the job of analysis. So predictive and proactive maintenance have the potential to allow companies to solve problems before they appear, which is, of course, very attractive for all of the issues that I mentioned before. So why isn't predictive maintenance widespread in industry these days? The benefits of predictive maintenance have not been sufficiently communicated so far, especially with regards to opportunities beyond traditional maintenance value drivers. So that's one issue we want to correct with the roadmap. Data ownership and data security issues were highlighted earlier on, I think, by Chris, and these are precisely two of the issues that need to be clarified before PDM will be widespreadly adopted, especially in multi-stakeholder value chains. But this is an issue that also underlies Industry 4.0 data value chains in any case. So that's very important for not only for predictive maintenance. It's still quite difficult to make data available, to bring it into the PDM system. That needs to be reduced. The reliability and the future proofing of PDM solutions needs to be improved to attract industrial customers. I think the reliability is more of a messaging issue, and the future proofing is something that we'll probably look in more detail in standardization. Speed and efficiency of replicability of PDM solutions across use cases and sectors needs to be increased. That is indeed quite a challenge, because these days mostly you look at individual use cases to I see something in the chat to replicate across there. That's sort of case-by-case implementations these days. The output of PDM systems need to be actionable decisions and solutions on the asset, factory, and enterprise level. So we really need to look at solutions that give us something very concrete and not just some kind of a graph. So looking at the phases of predictive maintenance, the structure of these slides will be more looking at the gaps and challenges, so what is missing, and the related key enablers, which we'll look at later in more detail. So there are different dilemmas that you face when digitalizing your assets for predictive maintenance. Do you retrofit your existing equipment, or do you buy new equipment? Do you start from the data or start from the problem? So maybe you have a maintenance problem, you want to start from that, but you need to retrofit or buy the equipment to solve that problem, to get the data, or you already have the data and want to know what you can do with it. And then hardware versus IoT platform driven. So either you look at the vendor who provides your hardware and produces the data, or you look at the IoT platform provider and do it the other way around. The gaps and challenges in this area is that the market is dominated by digitalization solutions, which often lead to vendor lock-in and are quite inefficient, especially for SMEs. So we need open, flexible, and vendor-agnostic architectures to maximize the benefit of the digitalization strategies for the majority of stakeholders in the value chains. And it shouldn't be an end in itself, but it should always be aligned with a comprehensive digital business strategy. So it's no real use digitalizing your production line just to do maintenance. It's better to encapsulate that in an overall digitalization strategy, of which predictive maintenance might be one pillar. The related key enablers, which we'll see later, are Internet of Things and the Industrial Internet of Things, and standardization and interoperability. Detection and prediction, of course, are the two main cornerstones. So once you have the data coming from your data, you can detect its current condition. And on the basis of the historical data streaming into the predictive maintenance system, doing data analysis, you can predict what is going to happen. Problems here are that prediction algorithms and the AI algorithms there are not always robust, verifiable, and validated. This really needs to be implemented for widespread industrial adoption. So you need to understand what is going on in the IT system and why it is actually producing some kind of a forecast. Causal diagnostics require problem-specific expert knowledge. Just having data, just having a data analytics output is not enough. You need engineering expertise to understand what that actually means in terms of maintenance action. So you really need to combine the skill sets of data scientists and engineers. Solutions are not always integrative these days. That means that we need modular concepts, modular systems that are able to integrate different components to create holistic predictive maintenance systems. And one thing sort of coming out of the corona crisis is that we see that if you don't have any data and no data is being produced, you can't train your predictive maintenance algorithms. And one idea there is to have data marketplaces where you can use anonymized data to quickly bring your system up to speed. Key enablers here are data-driven analytics, proactive computing, and of course, skilling the personnel. Actionable decisions are what need to come out of the predictive maintenance system. So the system really needs to tell you what you have to do. There are two pathways to these kinds of decisions, really. The first one is what I just mentioned. Maintenance experts can interpret graphs and results from the predictive maintenance system based on their knowledge and experience, but we want to move towards PDM systems that recommend the best maintenance actions proactively. The gaps here are that, again, the interpretation of the results require engineering and data science skills combined. These skill profiles are quite heterogeneous in maintenance, making it difficult to really upskill all of the people involved. So the solutions providing clear, actionable, and comprehensible maintenance decisions are needed. This, of course, has to be somehow encoded as rules into the system. Making it difficult to update predictive maintenance systems throughout the running of the system. So supervised self-learning loops are an idea to keep updating the rule base in the predictive maintenance system to optimize and improve maintenance recommendations, having the humans and the experts in the loop. What we really need is context-aware maintenance instructions at all levels of maintenance and the appropriate human-machine interaction technologies for that. Some of them have been used in some of the projects in the 4C cluster, like augmented reality, virtual reality, digital intelligent assistants are an upcoming trend. Of course, the digital twins and advanced visualization capabilities. The related key enablers to provide actionable decisions on all levels of maintenance are proactive computing, AR, VR, digital intelligent assistants, digital twins, and skilling of personnel. Standardization and interoperability. PDM solutions need to be seamlessly interoperable with your entire IT ecosystem in your company to ensure maximum benefit. For that, we can leverage and extend existing maintenance relevant standards to ensure process and IT interoperability in the maintenance processes. We can use advanced semantic models for PDM, which aren't there yet. We'll see that later on in Yves and I think Hugo's presentation. These are required for a future-proof cross-domain interoperability. Reliable recommendations about technical standards for industrial Internet of Things ecosystems are also needed for future-proofing predictive maintenance. And of course, the related key enabler here is standardization and interoperability. This is our 4C system architecture, which I think in the interest of time, I won't go into too much detail about. I would recommend you take a look at it in the roadmap under the link that Cosmas gave you earlier. This is a synthesis of all of the architectures developed in the 4C cluster. We're looking at all of the phases that I just described, and yes, I think it's better to move on here, but if you're interested in how we see predictive maintenance technical solution, then this is a reference architecture that we developed across all of the projects, and also contained in the roadmap is how this maps to the RAMI 4.0 reference architecture. So I will conclude now with our vision of predictive maintenance. So what we're looking for is a standard-based, seamlessly interoperable PDM system which maximizes benefit throughout the company. We want future-proof cross-domain interoperability based on semantic models for predictive maintenance. At the same time, we are aware that we need to develop the required skills at the intersection of engineering and data science. Even though we want proactive, actionable, and explainable maintenance decisions incorporating these supervised self-learning loops. We need context-aware, human-centric, and intuitive interaction in open, flexible, modular, integrative, and vendor-agnostic systems and architectures. We need to have the algorithms and of detection and diagnosis made explainable and predictable. Explainable AI and augmented analytics are two keywords there. And we need to incorporate predictive maintenance into broader digital business strategies. Just finally, slide that I closed our final review and outlook with, looking towards Industry 5.0. We heard some of these topics in Chris's presentation. Predictive maintenance is already a contributor to many of these topics in coming up in Industry 4.0, which is no longer just a technological vision, but also one that addresses sustainability, resilience, and human centricity. So predictive maintenance, as I mentioned earlier, helps create more sustainable manufacturing and logistics systems by extending the remaining useful life of assets. It helps build more resilient industrial systems by helping systems react ahead of time in companies, so contributing to the autonomous smart factory that we heard about earlier, and more human-centric maintenance processes and improved workers' well-being by helping and assisting and keeping the humans in the loop of the maintenance processes. So thank you. That was our vision for predictive maintenance from the 4C cluster, and I'm sure you will see some of the topics that I mentioned picked up in the next presentations. Thank you.
Thanks a lot, Carl, for the very comprehensive presentation and the effort made in the 15 minutes to summarize this broad topic. We appreciate a lot the effort, and I hope you clarified a lot, the majority, of the topics we have been discussing. Thanks a lot again. Let me then introduce the next speaker, which is from FIDIA, Michele Surico, who will be talking about how we have been thinking about key enablers for predictive maintenance in manufacturing. So Michele, thanks a lot for being with us, and the floor is yours.
Hello, Sotiris. Thanks for the introduction. Can you see my screen now?
Yes, Michele, we can see.
Perfect. Hello, my name is Michele Surico. I work for FIDIA SPA, and I am the coordinator of the programs project. I'm just now going to introduce you some of the key enablers for predictive maintenance in manufacturing. So it is clear, if you're here now listening to this presentation, that you know that predictive maintenance may represent a powerful tool to aid all the manufacturers in making easier their work in relevance, in relative to the maintenance, by reducing costs and increasing the productivity. So it's no surprise that organizations are looking for effective ways to move and to approach predictive maintenance. The work that we did in the 4C cluster allowed to identify several enablers that can help the companies and the people to ensure efficiency and effectiveness while using this novel approach. Now, here on this page, you can see a list of the enablers that we found out. It is clear that this list is not meant to be full comprehensive. It only represents what we have been consistently using through the 6 projects that are part of the 4C cluster, even if, of course, with different degrees of use. And I will skim through these enablers during this presentation, leaving out only the last one, standardization, which will have a dedicated presentation given its importance as enablers for predictive maintenance. So regarding the industrial Internet of Things, it is clear that it is probably the first enabler from which we should start from, because it allows to connect everything at factory level and even above, from individual sensors to machine to whole factories. The point is that implementing IIoT capabilities is difficult even when you consider an equipment which is not yet existing, so which you are still designing. And when you deal with legacy equipment which is already existing, it can be even more difficult. In this case, we talk about retrofitting solution. That means using usually third-party solution to extend the capability of existing equipment. This solution include IoT platform, gateways, and sensor used to measure KPIs and make this data available to the remainder of the platform. The core of this retrofitting, but also of the fitting of new equipment, is of course the sensor. Now, existing production equipment already includes a standard instrumentation, because without measuring, you can control any kind of process. So there are a lot of sensors already pre-installed on this standard equipment. We're talking about sensor for position, for pressure, velocity, any kind of fundamental parameters that are usually accessed already by PLCs, controllers, whatever is on existing system. And these are information which most manufacturing engineers are already fairly compliant. They know well them. And so adding capability for monitoring this kind of data could be just a very simple task, by adding channels that allows to correlate these data systems, this sensor, with the rest of the performance data analysis systems. It is clear that when choosing the best sensor that have to be maybe added to an equipment, if you are thinking about measuring new variables, or just retrofitting them by an alternative methods to make this data available to a centralized measuring platform. The point, it is important to note that the problem of integration should not be misunderstood, because we have two possibilities. We can ask for support from external companies or make an integration in-house. And it is not easy to say which is the lower cost option, because it really depends on your system. And modern sensors that we could decide to buy are usually coming with already integrated signal conditioning and analogic digital conversion, while retrofitting solution could require adding amplification of signals, analogic digital converter, and so on. Really, the choice of which solution to apply, if to buy new sensors or to retrofit existing ones, really depends on the kind of solution which are already present on the existing equipment. And once we have this sensor, we need to connect them to a network, because this is the logical extension of a fully instrumented factory. So an IoT gateway is a tool that allows to aggregate sensor data, translate between the sensor protocols, and sending there where they are meant to be used. That could be even in the cloud if we use internet as a way of communication. And existing equipment can be tied into this network very simply using this kind of gateways, even for older machine. Such machine that could be limited to all the 24-volt signals or serial lines. There are gateways that are capable of converting this information into more modern protocols, for example, MQTT, and then transmit this data when this data is meant to be used. And once we have this data, we have collected them, we have sent them, we need to exploit it. And for it, we need an IoT platform, which is basically an operative system for the IoT that connects the sensor and the equipment and all the infrastructure necessary. Thanks to the IoT platform, analytics can be run at different level. It may be at machine level, at manufacturing level, or even for entire factories and network of factories. Clearly, in this case, it is better to use something which is deployed on the cloud in order to save a part of the cost of the whole infrastructure. And it is worth noting that some of these platforms are offered as a service, which allows some advantages in terms of cost, scalability, and support for the whole product. Once we have collected all the information and moved them into a good spot, we need to analyze, of course, this data. And so the two main key enablers for this kind of topic are, of course, data-driven analytics and digital twin. The first one is, of course, data-driven analytics, because predictive maintenance can be enabled by this predictive analytics. This particular approach can be seen as a black box that is capable of automatically learning the system behavior from the collected monitoring data, vibration, acoustic signals, force, pressure, whatever you have it, you drop it into these kind of tools and they try to learn which is the nominal behavior of the system. And rely on the assumption that this characteristic of the system remain unchanged unless a malfunction occurs. It is possible to use this system to detect deviation from nominal behavior. The most well-known of this kind of pattern recognition techniques is machine learning, that is used to assess the current assets of and estimate the remaining useful time. Machine learning is a branch of artificial intelligence based on the idea that system can learn from data, identify patterns, and make decisions with minimal human intervention. Now, machine learning, as you can see from the scheme on the right of the picture, comprises several different approaches. It would require a dedicated webinar only to skim through this, but you can find some details about all this in the white paper, which I strongly encourage you to download and read. Another approach to exploit the data collected from the sensor is the digital twins. It is a concept that stands for an actionable simulation that not only comprises the components geometry, but it also includes its behavior. So a digital twin is comprised by a reflection of the physical component or system that you want to model, the representation of its design and configuration, and the ability to predict the physical system behavior. Now, the main limit of the digital twins is that currently there is no widely accepted definition or reference architecture for digital twins. So these applications are usually very use case or asset specific dependent, and are quite difficult sometimes to transfer these models to different areas. Nonetheless, digital twins are very highly relevant for predictive maintenance because their characteristic, which is the capability of representing a system design, monitoring its state, and anticipating its behavior, are fundamental for any predictive maintenance approach. Another enabler is the proactive computing, which is an evolution away from interactive computing toward a human unsupervised computing scenarios. In this context, proactive computing is an enabler because it enables the detection of equipment abnormal behaviors, the prediction of future failure modes, and most important, the decision about optimal action that can eliminate or mitigate the impact of future failures. Hence the name proactive. Also, augmented and virtual reality can be seen as enablers for predictive maintenance because they enable the transfer of knowledge without location boundaries. Augmented reality and virtual reality functionalities in the manufacturing maintenance field serve several goals. They support the machine operators to easily understand and diagnose which are the problems. They increase the safety of the maintenance task and enable remotely supported maintenance, which is very important in this period in which we can ill afford sending people to different locations to perform maintenance. Another enabler is, of course, linked data, which in the frame of predictive maintenance means linking and correlating different heterogeneous available data sources to make them more useful. And a typical approach to leverage linked data in the concept of a predictive maintenance platform deals with the explorative visual analytics, because these particular types of human-machine interfaces allow to visualize data in a customer-oriented way, allowing the user to monitor and interact with the data both in real time and asynchronous. Finally, least but definitely not the least, is the enabler for predictive maintenance is the skilling of personnel. I hope it is clear by now that deployment of predictive maintenance on a production line involves a wide set of activities. And so skilling of personnel could be required when covering the competencies required for the implementation of predictive maintenance, because we need people capable of defining what is the predictive maintenance application, including the selection of the best approach for the prediction, the creation and maintaining of the models, the definition of which data is required at each stage of the predictive maintenance, deployment of the solution, validation of the models or algorithms. We need people to collect and manage the data, including the installation from the hardware and software point of view of sensor, gateway, network infrastructure, the cleaning and formatting of the data, as well as making this data available to the stakeholders. And finally, we need people capable of embedding predictive maintenance at all levels of the organization, because this phase is fundamental to scale and embed the solution, the prediction that we made with predictive maintenance with day-to-day operation. And so we need the skills from the capability of deciding if, how, and when the components should be maintained, to the integration of maintenance with production schedules, to the forwarding of the maintenance related information to the relevant people in the production and management structure. While some of these skills are usually available into a traditional industrial environment, most of them can be considered quite new, because they extend far outside the normal boundaries on competencies which are usually available in nowadays factories. That's why the addition of the dedicated predictive maintenance personnel or the upskilling of existing personnel is required. However, it is worth noting to ease the scare that I may put on you about the skilling of personnel is the fact that most of such skills are required during the setup of the predictive maintenance solution, and much less after they have been properly tested and validated. So for smaller companies, for SMEs, it may be worth, instead of hiring dedicated predictive maintenance personnel, instead buying a customized predictive maintenance solution as a service, because it would make a much more economical, easier for companies to be introduced in the world of predictive maintenance. Now, this closes the last of the key enablers which I wanted to present. You will find, of course, much more detailed explanation and information inside the white paper that the 4C cluster produced. I just want to thank you for listening to this presentation. Thanks all the friends in the 4C cluster that contributed to the creation of this presentation, and of course the relevant chapter in the roadmap, and also into the research report argument for robust predictive maintenance systems on engineering.com, which provides a lot of useful information about retrofitting legacy equipment with the PDM solution. This is all. Thank you.
Great, Michele. Thanks a lot for the energy and keeping up with the time. You present us a lot of content, and thanks a lot. That was Michele Suricoro from FIDIA, coordinator of the programs project, while before we had Karl Siebering from BIBA, coordinator of the uptime project. The next one that will take us even more into practical demonstration of what the cluster has been doing is Nikos Nikolakis from LMS, manager of the Serena project. Nikos, please, the floor is yours.
Thank you, Sotiris. Good morning to everyone. Good morning to the people in our audience. Give me a second on my screen. I don't get the feedback, so let me close the video just in case the bandwidth is not enough.
I don't know, Nikos, if you can hear us. Maybe.
So there is.
Yeah.
So there is. I can hear you. Sorry, but my system is stuck. They cannot control anything. Sorry for the delay.
Nikos, if you want, maybe we can release you for now and change a little bit so that you can control things. Maybe we can move to the next one and interchange the sequence. I don't know if Basim is already available and can take us through the next chapter, and then we can probably return to Nikos. Basim, are you available? Are you?
Yes, I'm available, but it seems to be I cannot share my presentation. Will you help me from your side? It needs permission from you.
Yes, yes. Let's wait for a second. Nikos has to release the sharing.
Yeah.
And Basim then will continue from the pre-com project.
It's still Nikos trying to share.
Let's hope now it is released.
Okay, let us see. Yeah, yes, I have my possibility to share. Do you see my screen?
It's all good. Yes, yes, Basim.
Yeah, perfect.
Please about the chapter on roadmap for industry practitioners. Please, the floor is yours.
Yeah, thank you very much. Yeah, my name is Basim Al-Najjar. I'm professor of Technology, Linnaeus University, and coordinator of pre-com project. In my presentation concerning roadmap for industrial practitioner, I will cover the following aspect in my agenda. Briefly about the objectives and development of smart predictive maintenance, approaches of predictive maintenance, goals of applying maintenance, smarter predictive maintenance from operability, performance, and technology point of views, return on investments and maintenance, and practitioner checklist. The objectives, the main objective of the whole project is actually to increase in-service efficiency cost effectively. This leads to that the cluster projects aim to deploy, test, and demonstrate smart predictive maintenance, able to identify, localize damages, that's to say, to tell the end user in which machine there is a damage and in which component, instead of searching for problem, and also to assess the severity of the damage, predict its development in the close future, and assess the remaining asset life, which is very important for planning next production order, reduce the probability of failures, unnecessary stoppages, and false alarms. In many cases, false alarms are actually equivalent to stoppage due to failures, and then to optimize maintenance with respect to maintaining continuity in the production plant, allow follow-up maintenance and the production performance from both technical and economic point of views, digitalize, automate manual data, and secure data quality. In many cases, not all data available at the industrial site are digitalized, and looking for digitalizing data, we need to have special tools for that, which has been developed and practiced in the pre-com. Maintaining machine quality, it means that maintaining the technical specification of the machine, shortening downtime, is a production maintenance action, secure production planning and continuity in order to enhance productivity and profitability of the component of the company. Development of smart predictive maintenance. First of all, it's necessary to identify what machines which are critical for the production, and their significant components means that the components of dangerous or costly failures. And also we need to define and determine a smart predictive maintenance system concept and design with an overview plan showing how the concept will work in the future and what possible functions will be provided by this system, types of data necessary and the data follow-up. And then we have to design concretely the system, and its functionality in collaboration with the end user, because at the end of the day, the one who will use the system is the company, and we should take in consideration their demands, needs, and challenges to be covered by the system. Developed and adapt all technologies. That means that all modules, tools incorporated in the system developments should be somehow accommodated with respect to the end user, and all connected to the cloud using intelligence tool, such as we call it a pre-con brain. And this is very necessary in order to control data flow, recommendations, and reduce the probability of streaming data to the end user when it's not necessary. And then all these modules should be tested at lab in order to verify and validate them in addition to the overall system. Finally, the system should be demonstrated using the monitoring process and evaluate its impact on the tested site. Machine Builder has been involved in our project effectively, and the idea is to have the Machine Builder machine user and maintenance technology. At the end, the machine user will receive also information describing failure data, which can be very interesting underlying information for modifying the existing machine or developing a new generation of the machine. The smart predictive maintenance module subsystems can be exploited either as a whole or partly based on what type of function that needed to be utilized by the system. Approaches of predictive maintenance, I will not discuss this standardized figure of maintenance, focus only on the predictive part. From our point of view and experience and application, industrial application, we found that predictive maintenance can be achieved or developed in 3 different ways at least. One is totally statistical modeling based, such as big data analytics, or it can be also based on engineering approach, deterministic. What we found it will be much more interesting is to combine these 2 approaches using statistical approach and deterministic approach, because in our experience and result of the project, it is not easy to describe reality using only one statistical model or one experience. Combination of both is very important, useful, and beneficial. To select a system, there are some issues to be considered. First of all, if the system itself, smart predictive maintenance system concept and design fit the company infrastructure, it means that it can be integrated in the company system. The system objective concern and accuracy, it means that is the system designed for detecting damage at an early stage is necessary and okay for the company? Does it enable damage follow-up to avoid any unnecessary stop or sudden failure? Does it provide enough lead time to act when an action is necessary to avoid unnecessary stoppage and shortening the stoppage time? Does the accuracy of detection and recommendation acceptable because it has direct impact on the production planning and the production time? Does the area of application of the system cover company's process and environment? Does the data and its format demands available in the format or the type of the data? And if it is not, can be achieved later on. Goals of applying smart predictive maintenance. The major goal actually is to approach what we call it e-maintenance 4.0, meeting the demands of Industry 4.0 through the following. The reason is when we have Industry 4.0 implemented, everything will be digitalized and automated, and the maintenance should also follow the same direction. Otherwise, the losses in the production process will be huge and cannot be avoided. And some of these issues should be considered is ability of the maintenance system to maintain the quality, the technical specification of the manufacturing machine and support machine. Getting better and on-time control of the condition. It's very important, at least to secure conducting the production plan and continuing production without any problem, reducing the probability of failures, unnecessarily stoppage, and there was related accidents, which is represent in some cases a big amount of the total production time, at least in some studies done in Sweden, shown that we are losing about 30 to 40% of the total capacity designed in the machine due to different type of stoppage. And some part of this percentage related to maintenance and maintenance related to stoppages and accident. Easing conducting maintenance action. For example, in many cases, there are very specified technicians for specific task of maintenance, but we found that applying augmented reality with relevant information and ability of communication, taking photos and videos and sending information, receiving information, reduce a lot of the downtime, and at the same time allow any technician to take the task even if it's not done before, which reduce the necessity for keeping only the same person doing the same task, and in the case he was sick or retired or not available, the whole production line will stop, or the whole machine function will stop because of that. Reducing losses in energy and material, which is very important, and influencing the production cost, and at the end will influence profitability or the profit margin. Enhancing working environment and consequently personal health, such as reducing humidity, reducing vibration and temperature. Environmental effect is very important to be considered as well. And at the end, it will be enhancing the production continuity, reduce production and maintenance cost, and its impact on business, and consequently increase profitability and competitiveness. Operability, performance, and technology of predictive maintenance. If we look at the operability of predictive maintenance, we can see that we try to let the system gather all data, and what I mean by all data, relevant data, well-defined data from the beginning, from all related working areas such as machine, production, operation, quality, energy, material. It means that the data that has been already decided from the beginning to be collected. It uses either a probabilistic or deterministic or combination, and also in the pre-com we used both of these approaches integrated in one system. The cluster project evaluated with respect to several key issues which are very important for any manufacturing company. Of these are maintainability. It means that the time need to maintain a machine related to the downtime time between maintenance, for example. Availability, how long time the machine will be available, and work safety, the impact of the machine operation and the problems on the human being safety, environment safety, and machine safety, material and energy losses, cost and payoff possibility, which is very interesting nowadays. The company cannot just apply a new technology just as a matter of fashion issue, rather than to realize how much it will cost and how much it will pay back and how long time the payment will be done. And this is very motivating later on for implementing any new technology. Environmental impact, and it's very important at the hot spot around the world, benefits and expectation of applying predictive maintenance. The evaluation highlighted an impressive positive impact on the key performance indicators, and more details about that you can find in the white paper describing in figures how much the changes achieved in the project, and numerically and in percent. Performance and technology. One or more of condition monitoring parameters, including the time to failure, are very interesting to be included. And the reason for that is to expand the range of covering all different type of deterioration in the process and all type of components, rotating and non-rotating components. And to involve wireless, wired, and embedded sensors, because not always it's possible to use wireless sensors due to the circumstances and surrounding and the disturbances. And PLC are necessary for gathering data in order to detecting deviation in the conditions such as a damage at an early stage. And we also realized augmented reality shown very potential benefit for enhancing maintainability, shortening the time of downtime for repair and shortening the time of training new technicians. Artificial intelligence, machine learning are very important for controlling data flow, securing communication, preventing streaming of recommendations and warnings, and providing on-time right recommendations, readjusting parameters and warning levels at need. For example, at failures, because it's impossible just to avoid failures to 100% is unrealistic, but when the system enabled automatically to readjust itself when such failure happened, to change the warnings level will reduce the probability of repetition of the same failures. Cloud is very important for data gathering, for follow-up, calculation, control, and also to combine database and knowledge base in order to enhance the utilization of the system. Industrial Internet of Things, Industrial Internet of Service, gateways, big data analytics models for auto-detecting unhealthy sensor. As everyone knows, garbage in, garbage out. If you cannot secure the quality of input data, will not be easy to secure the output accuracy for detection, recommendation, and everything else. So all these are very important for automating predictive maintenance from data acquisition until recommendation. And one more is auto maintenance actions, as long as everything is done automatically by analysis, diagnosis, prediction, recommendation. And in some cases, it's possible to send work orders to some actuator to make some changes needed by the system in order to reduce deterioration rate, for example, reduce production speed or increase lubrication or add more grease. Return on investment, almost all technical losses, all technical variables describing the output of failures can be converted to money, but not all. Some of them are a bit difficult to have it in this way. But for example, failures, accident, unnecessary stoppage, all these can be done. Integration, augmented reality, shortening repair time, and this in prolonging the production time, reduce energy and material losses, and also maintaining machine quality. It means maintain the invested capital in the machine. It's always necessary to have specific modules for assessing maintenance, technical and economic impact. The reason behind that, available accountancy system and program does not consider maintenance more than cost. So the whole maintenance budget is cost. And finally, the list for a practitioner. It's a set of questions highlighting the answer, the beneficial of having, for example, clear and written maintenance strategies not available always, and also how to maintain quality of maintenance of manufacturing asset, whether it is something beneficial. If maintenance considered able to reduce failure stoppages to enhance productivity and profitability. If it is beneficial having a maintenance strategy meeting the needs of Industry 4.0. If it is okay to having auto damage detection, localization, estimation, follow-up, prediction, recommendation, and recommendation of where, why, how, and when to act, which is very important for accurately planning and conducting maintenance actions. If it is beneficial to develop knowledge base in addition to the database, and also if it is beneficial to control and reduce energy and material consumption and their losses, and to improve environment work through reducing temperature, noise, and if it is also beneficial to reduce environmental effect for the company through more efficient maintenance. And that was the last slide for me. Thank you very much for your attention. More information you can find in chapter 6 in the white paper. And I leave the word to Sotiros. Thank you, Sotiros.
Thanks a lot, Basim, taking us through this complicated ecosystem of talking about how practitioners can employ the technology and make some real-world application. Thanks a lot for summarizing and all the contributors for sharing their experiences from the projects. Then we can move on with the next item, which will be from the colleagues from Uptime, it's Eve, and then from ZBreak, Hugo. To talk to us about standardization aspects of predictive maintenance. So at this stage, I would like to ask Eve to take the floor, take us through the standardization and how we have experienced that. Please, Eve.
Yes, thank you, Sotiris. I'm trying to share my screen, but I think Basim has to stop sharing, or I don't know.
Yes, I think Basim can stop sharing the screen.
Okay. It's not possible. It's if Basim can stop sharing, because or
yeah.
Okay. Thank you. Thank you, Sotiris. Thank you, everybody, to attend to this this event. Can you see my screen? Can you see my screen? Yes. Can you hear me? Well, okay. So my topic will be the standardization aspect of predictive maintenance. As we have seen with Carl, for instance, there is a lot of expectation of standards to implement predictive maintenance. So this is the agenda I propose you with first to give our aim, our objectives, the why of this collective work at the 4C cluster concerning standards. After, I will give you a small landscape of standardization for predictive maintenance. And I will address also the topic of maintenance semantics. We have seen that advanced semantic models are necessary to really implement predictive maintenance. Next, I will describe the methodology to follow the different standards we have to follow for predictive maintenance implementation. After, I will give the floor to Hugo Faria for Innova Plus, who will describe how 4C cluster project have implemented standards and the benefits they drawn for this implementation. And after, I will give a few words about the future activities. So our aim at the 4C cluster was to, of course, enable the platforms, the predictive data maintenance platform developed by each project to reach their market and to extend their market, and with standards compliant platforms. Our aim is also to contribute to standards update and also to future standards. We have seen that we have a lot of initiatives right now towards industry of the future, and we need also future standards in a digital world. And last but not least, our intent is simply to bring some light to practitioners and leverage their knowledge, giving some skills in these new domains for integration of data, thanks to advanced interoperability standards. First, some words about the landscape. It's quite a complex landscape, actually, because we have, yes, main standards development organizations, like ISO, IEC, ETU, also at the international level, but we have also European standardizations committees and also national ones. There are links together, but there are different technical committees. For instance, for maintenance, we see at least 3 technical committees in ISO. We have also at the European Committee for Standardization 1 main TC 319 for maintenance. And we have also in IEC and the European counterpart some standards on dependability, for instance, and also all the national standards. For instance, for the TC 319, you can see the bunch of standards developed by at the European level with the basis on maintenance terminology and also the maintenance processes and indicators. And I will not go into too much detail. But as we have seen, for predictive maintenance is not only a subdomain of inspection, it is a domain which need holistic, or I prefer maybe a systemic approach. And so we have to look at also different industrial domains. For instance, in oil and gas industry, there is ISO 14224 about maintenance reliability data, which is very used. And also we have also, for instance, standard technical committee about measurements. We have also a joint technical committee about information technology, which is also developing some standard for digital twin. We mentioned before as a key technology for the future. And we have also the ISO TC 184 about industrial data, which is also working on the digital twin framework with new draft for digital twin. And last but not least, maybe I mentioned the common standards, which it's now maybe 30 years old, and since more than 10 years, it's a common ISO and IEC standards. It's 81346, which is called Reference Designation System, which gives very simple and clear rules to address the complexity of a system. And so I think it's a very important one as a framework to manage information about a production system, whatever the domain, industrial domain, whatever the engineering disciplines who produce the data. And yes, we need more advanced semantic models. We have already some, but they are not sufficient. And we know that practitioners consider terminology issues are a barrier to interoperability. And I think it's a reason why at the 4C cluster level, with Soteris and Cosmas, so Van Vallis, we decided to make a comparison of terms of maintenance from various standards. So we identified more than 500 terms and to look more carefully to the definition of 68 terms from different standards dealing with maintenance terminology. Here you have the list of these standards. And as you can see, they are from different standard organization and technical committees. For instance, here we have the definition for some of these terms. And I draw your attention that the year of edition of the standard is important, because in the different versions, different years, you have different definitions. And the good news is that we can observe some convergence also in these definitions. But there is a lot of questions when we look carefully at this definition. So it's important to start from dissensus also before going straight to a consensus of a term, because sometimes it is justified to have different meanings behind one term, and so you have to identify the context of use of a term. And there is also how can we what about the definitions of terms which are not specific to maintenance, or generic terms, and how we proceed when they are not defined as a standard. We have to look at other standards, more generic standards. And for the future, we recommend to go back to the context, to the concepts and the use of the concepts, and not only how these concepts operate and are important, are useful for the maintenance and the production people, and also understand them in this context of use in a dynamic way, I would say, and to better identify commonalities, but from a background of difference in a kind of bottom-up approach. After, yes, we can use formal ontology for generic ontology, top-level ontology, I don't know, local formal ontology, and also domain-specific ontology linked to this more formal ontology. So, to follow up all this landscape and moving landscape, by the way, we put in place a methodology used in aeronautics to the radar chart methodology with, as you can see, 4 quadrants depending on the level of maturity of the standards and the level of involvement of the ecosystem to develop new standards, and 3 levels if these standards are adopted, candidate, or on track. And here you have this kind of radar chart where we put some topics of maintenance, the business aspect, and as you can see, there are many. You will find in the Annex 2 of the white paper the complete list of maintenance-related standards we have identified, and yes, we have a color code for the different types of standards. And here we have more data-related standards, but business, as we have seen, as it was said before, it's important to make a link between business data and their representation in data formats and so on. And here, for instance, as you can see, there is standards mentioned by Chris DeCuber, OPC-UA and GSI, but also MQP, MQTT, which are very helpful and to make components of predictive maintenance platform interoperable and open to new functionalities. So I will give the floor to Hugo, and we'll move the slide if it's okay for Hugo to.
Yes, thank you. Good morning to all. Indeed, we assessed all the implications of standardizations in the 6 projects of the 4C cluster, and without much surprise, we divided this subtopics into 2 classes, as was just presented in the slides before. So the data-related ones showed us that the common topics that are addressed or required to be addressed cover communication, data modeling, security, and connectivity. So all about the flow and the formatting and the compatibility of the data and the connections. And then we classified the application of standards that are very specific for maintenance on the technical side. Next, please. And therefore, the 6 projects brought their use cases, and I mean real use cases for the projects, and a few were selected by each project to showcase the requirements of standardization and moreover the advantages of standardization. Next, please. So we have in the left-hand side the list of projects, the 6 projects that were directly involved in this methodology. And we have in the table a just brief indication of the main standards that were identified, applied, and then benefiting the specific use cases in each of these projects. We can see, for instance, that for the programs project, we have a few implications on offering better precision on life cycle cost assessment, for instance, and selection of components for predictive maintenance, effective machine learning using this data mining group set of standards was also addressed. Mimosa set of standards in the Serena use case that were highlighted in our methodology. In the Z-break, the formatting of the data that was collected at shop floor level independently of the kind of assets and user level, so that we could, in an harmonized way, indeed, use this data throughout the platform and the different modules of the platform. A prophecy for the HAMI 4.0 with benefiting from this standardized digital representation of the physical assets. UMATI for the PRECOM project, whereas communication was found to be critical aspect. And in the uptime project, we had this AMQP and MQTT and other standards that are more directly related with the predictive maintenance solution itself. So the way to apply, to harmonize, and to anticipate future upgrades of the solution itself. So these were a few use cases that were brought in to showcase that not only we have a requirement for standardization, but of course trying to show, and we think we did it at an initial level, to showcase that indeed there is a clear benefit for this. Next, please. And this led us to a common vision and a common understanding that all of these contributed in each case and all together for to ease the process itself, to increase interoperability between different systems and machinery level and so on, and overall to improve the efficiency of the processes and even the programs themselves. So overall, the idea was to showcase, and we included in part this in our roadmap on a set of initiatives and suggestions on how to progress from here to the future. Thank you.
Thank you, Hugo, and thank you very much for the benefit of using standards in different projects. So for the future, we propose to maintain the effort on maintenance semantics to go towards an ontology of maintenance, what we call an ontology, common to different domains in industry, and also to update the radar chart, because the radar chart is a picture, a snapshot at a point in time, and also should be maintained. And also, I think it's important for standards to be digital also. So I think it's important to support the development and use of what ISO calls the standards machine, accessible, readable, and transferable. That means that standards embed a lot of knowledge, and this knowledge should be digitized and accessible to be computed by machines, and for instance, to check the compliance with requirements of standards, for instance. But and so that's an important point. We have seen that we have a lot of knowledge in existing standards, but they are in paper, old standards, I would say. And in the future, it's very important to digitize these standards as pieces of software of some sense, and regularly updated. We have seen that most of the projects we had in the 4C cluster were on existing production systems, and of course there is an important issue to be addressed, is to integrate the legacy data and applications. And this is not trivial, and this is really a difficult point, and which needs more future research agenda to really to be solved. We can use, as we have seen, IA, digital twin, more advanced mathematics for as it is done regularly in industry for maintenance, also as to use more and more statistics and things like that. But also some specific efforts should be made to compose the different models we have, to map maybe models to ontologies, to commands, and so on, but also to find a way to keep all the meaning of the data in a context, and both linked data technology will be also helpful, because a data by itself has no meaning, but has more and more rich meaning when linked to others. Thank you very much.
Great. Thanks, Steve and Hugo, for contributing to that presentation, and for collecting from all projects input on the complex item of standards. In the interest of time, let us move on. We have two remaining items that are rather interesting. One is on the use cases discussion. The second one will be on the future research directions. Let's try to invite again Nikos, that will take us through the use cases discussion. Nikos, please share us your views and what you think we have achieved with the projects in this class.
Thank you, Soteris. Sorry for the incident before. I will try to share my screen. Hope I have better luck. Just give me a second. And please confirm to me if you see my screen. Can you see my screen?
Because the screen is not here yet. Some changes. Now we see the screen. Now we can see the slide, yes.
Okay. So I cannot go into the presenter mode, I think. It doesn't allow me. So if you can see the slides as they are, I would like to continue as it is, if it stops breaking. Otherwise, I would like to ask Kosmas Alexopoulos to share the presentation. I can narrate it.
Sure, Nikos, yes. Let's give the sharing rights to Kosmas at this stage, and Nikos will take us through the content. Yes, Kosmas, we see now the slides. Thanks a lot. Now, maybe Nikos, you can go on.
Thank you, Kosmas. Again, sorry for the inconvenience. We can move on to the next slide. So in this presentation, we will go through what is included in the fourth chapter of the 4C white paper, and it is about the use cases. So pretty much in brief, it is how the vision of predictive maintenance that was presented, that was described at the beginning by Carl, as well as the key enabling technologies as were brought and introduced by each individual project, was materialized in the context of the industrial pilot cases that were brought in the 4C cluster but by its 6 projects. Next slide, please, Cosmas. Okay, so in brief, in the 4C cluster consists of 6 Horizon 2020 projects with a clear focus on predictive maintenance technologies in order to increase the operating life of the production systems of the individual use cases that were brought. So 6 projects, meaning 6 different methodologies, let's say, to enable predictive maintenance in the context of their industrial partners. 6 different approaches, which we will, as we will see in the next slides, have some commonalities, have some similar features. Nevertheless, this brings us to 18 industrial pilot cases, all reported in the context of the 4C cluster white paper. Getting into the overview of the pilot cases, we have 6 projects. Cosmas, this is an animation, so you can go on. So the 4C pilot cases cover pretty much a quite extended, a quite wide area of the European manufacturing sector, including partners from iron steel parts, manufacturing of high precision reduction gears, tissue paper manufacturer, metalworking machinery, from the automotive industry, from consumer products, from robotics, from white goods, from elevators, manufacture of elevators, steel industry, logistics, and packaging equipment. So what is the key message I would like to mention here is that the information that are included in our white paper, the 4C cluster white paper, do not apply only in a limited number of use cases and were not tested and validated only in a few cases. As you can see here, out of the 18 pilots that are covered in the white paper, the solutions, the generic ideas, the generic information that are included in the white paper have found applications in a wide sector of the European manufacturing world. Next slide, please, Cosmas. So in the next slides, we will just dive a bit deeper into what has been the motivation for the use cases, for getting into the projects and testing the solutions. Pretty much it is to increase the efficiency of their processes, to increase the predictability of failures, the availability of their machines, in order to reduce the production costs. Thus, through these 4, let's say, indicative indicators, to transform the maintenance activities into a strategic tool for their production processes in order to remain competitive, so within the European borders as well as in the foreign markets. Next slide, please. Each project, each one of the 6 projects followed had different technical key enabling technologies. Nevertheless, if we collect all of them and try to find some similarities, there are some basic steps that every project followed and pretty much applied in their use cases. So the first step was to identify what equipment, what were the assets to be monitored, and what were the critical failures that were important for the manufacturer. To deploy some IoT systems and achieve some connectivity between the assets and the systems and acquire data, thus gaining some insight on the underlying process. Then apply some edge and cloud processing modules, software and hardware, and try to figure out what the degradation mechanism is. either by creating differential equations, by physics models, by mathematical models, or by analyzing extensively the collected data. And then to facilitate maintenance activities and decision-making, integrate additional applications such as scheduling or process planning or operator support with augmented reality, virtual reality, or mixed reality techniques. And the glue, bringing everything together, in most cases was a cloud platform. Next slide, please. Now, let's check into greater detail how the pilots, how these 18 pilots are described in the 4C cluster white paper. So, taking as an example, an elevators manufacturer from Finland, the Kone company. We start by presenting the case, starting with the motivation, why this company needs to investigate some predictive maintenance approaches. So for the Kone case, they have an automatic metal sheet punching and bending production line where one of the faults they would be interested to figure out why it happens and to predict its occurrence is to detect bearing faults. And this is what is of interest for the end user. Then we provide the solution as provided by its project, the technical solution, bringing the system of the Serena, Precom, Prophecy, and deploy it on the premises of the use case. For example, for Kone, it included the installation of some data collection devices, software and hardware, a module to analyze the data, another software component to predict analytics, next to schedule the event, the maintenance event, and inform the appropriate maintenance personnel to carry out this activity. This included the scheduling of the event, the alarming of the maintenance personnel, and the provision of adequate information to support the maintenance procedure. Following the technical solution comes the benefit for the company, either materialized as an impact in form of KPIs. What is the benefit for them? What is the benefit for their production? So for Kone, for example, the impact was an increase of 100 minutes to their mean time between failures, which was rather important for them, as well as a 10% reduction of maintenance costs when it comes to this specific asset. And the lessons learned, what experience they gained, what experience they acquired, what knowledge was transferred to the end user. For the Kone case, again, the lesson that they learned out of the application of the respective project in their test bed was that the analytics can be performed on a low-cost edge devices, which in the specific case was a Raspberry Pi. And most importantly, that there is a gap in the skills between what is available in the shop floor and what predictive analytics and predictive maintenance needs. And specifically, it comes to the interpretation of predictive analytics, which is not easy. In the same way, all cases in the same chapter are structured. We will take in the next slide some indicative ones, just to show some more examples, and you can find more details in the related chapter in the white paper. So from the white goods manufacturers, we have Whirlpool MF from Italy. The first example is from the drum dryer production line. The motivation was to investigate the transition from preventive and reactive maintenance techniques that are currently available to predictive maintenance. The motivation for them was to enrich what they currently do and reduce the breakdowns of the equipment. Why? Because this is a waste of money to them. At the end of the testing and validation, it was noted an increase to their mean time between failures, a reduction of the MTTR, mean time to repair, which led to a reduction of the total cost for maintenance. A second process that was investigated had to do with the foaming process as part of the fabrication of refrigerators. The motivation for Whirlpool was to increase the availability of the machine and the efficiency of the foaming process. The assets that were of interest was the mixing head that was in charge for the foaming process. As a result of the testing and validation, Whirlpool reported more correctly, an increase to the overall equipment efficiency by 5.5%, a 15% reduction of mean time to repair, and an increase to the mean time between failures by 100%. This resulted in an estimated reduction of total cost of maintenance by 8,000 euros. Next slide, please. In a similar way, we have here a use case from Spain, from another project related to the milling machine, where the important was to check the condition and prevent unexpected failures. In a similar approach, the impact was quantified, and we see some benefit for this use case as well. More information, more quantified impact is included in the white paper. So in order not to waste time, let's move on. So in total, as overall, we can state that 10 pilots out of 18 have declared an improvement of TCM, 9 an improvement of overall equipment efficiency, 7 in MTTR, and 4 in MTBF. So we can see that there is some impact out of the solution, out of the technologies that are reported from each project. Next slide, please. So to conclude with my final slide, lessons learned. The analysis of the data model in order to discover the degradation mechanism and its causes is pretty complex. It's a tough task, and based on the reports and the use cases, this is something difficult to accomplish. It requires a lot of effort, and it's a complex task. Both data experts and process engineers are required. Why? Because their knowledges need to be complemented in order to discover and identify anomalies in the data and in the behavior of its equipment. The most important part is that in order to predict some anomaly, to predict a failure, and as we have all learned in the tough way, the hard way, we need data of appropriate quality and of adequate quantity in order to be able to predict an anomaly. It is a challenge to integrate different technologies into a single platform, make every system, every heterogeneous system to work together. But if we can come up with a conclusion that can be supported by the findings of the white paper, the predictive maintenance can reduce costs, at least as reported, and thus can be supported by the 18 pilot cases. This is the final outcome of my presentation.
Thanks a lot, Nikos. Indeed, all projects have been driving the effort on the basis of industry, industrial needs. And also, I think you try to summarize the achieved benefits, at least the direct ones, and also lessons learned have been very important. Thanks a lot for that. Of course, we learned a lot. We expect to do a lot of things in the future. We hope some messages are already clear from the presentations. But also John Soldatos from the Prophecy Project may take the word and summarize a few things on what we could be doing in the future. So please, John, the floor is yours.
Thank you very much, Sotiris. I hope you can see my slides. A lot of the things all mentioned so far being standardized, so things stemming from the use cases, the standards, and so on. Just a little disclaimer here before going into the details. Our cluster was dedicated to predictive maintenance. So all these projects all the 6 projects had their work, the focal point of their work was condition-based maintenance, predictive maintenance. So that's where also our recommendations are focused. So we are not, dealing with wider issues where maintenance is also very relevant, like quality management or decarbonization, or a lot of things on the twin transition. So this is one thing, and another thing is that we completed the white paper a while ago. So a few months ago, so if you might be looking for some fancy things that are discussed, during the last 6 months, you won't find them there. But I'll try to, give a perspective for this as well. So we have a recommendation on data. We say it's the oil of Industry 4.0, but working as projects. we realized that access to industrial data is not yet easy, is not yet seamless, and especially when you want more structured data, clean data, data that are proper for being fed into algorithms. So when our project started, we saw some research from McKinsey saying that, okay, almost 1% of industrial data are used. So we really need initiatives for getting and using most of this data, both for production applications, but also for research. It is very important that researchers, innovators have easy access to data sets that they can use in their research. So there is a need for some process and structuring that. A link to this, I think we, as project, we appreciated the value of maintenance test beds, right? So, you can think of pilot lines. Of course, there are digital innovation hubs that provide such experimental facilities, but you need something like this because you need a lot of tweaking of things before they going into production. Now, another thing which comes on the learning side, in general, you can take advantage. I think predictive maintenance and condition-based maintenance, and also prescriptive maintenance that was mentioned before. All of these are data science games, okay, data analytics games. So all our projects used a lot of machine learning, deep learning in doing this. And I think it really makes sense to make this process more accessible to the domain expert. So to the people that they are actually working in the factory, and not without the deep involvement of machine learning expert or data scientists. So to this end, there are developments in the machine learning space, AutoML, explainable artificial intelligence, and so on. So all these are good approaches for making this accessible to the domain experts, so to the people working in the factory as maintenance workers, maintenance engineers, industrial engineers, and so on. So that's one more recommendation. I think you've listened a lot about the interoperability topic and standards previously, like Mimosa and so on. This remains, although a lot has been done, right? This remains a challenging problem, right? Because you've got to solve it at multiple levels. You've got to address the different semantics, and if you want, systems that are really autonomous, I'll talk about them in a while. You really need also to have good semantics so that you have, process level or business level interoperability beyond harmonizing some data formats, which is probably the first thing you are doing when you are collecting and putting together data from different automation systems, production systems, business information systems, and so on. A very important recommendation concerns the business modeling. So we've seen that predictive maintenance and condition-based maintenance has a lot of potential for disrupting how business is done in this space. So it is really possible to support models like asset as a service or maintenance as a service. However, even these, sound straightforward technically, when it boils down to study all this in the business perspective, it turns out that there are a lot of complications, like IP owner systems, IP data ownership issues. Also, another very important thing is what are the stakeholders for this, for which these new business models are destined for? So is it the OM for the asset as a service, and what are the roles of the integrators, of the manufacturers in this new value chain? So we know that this is looked seriously also by machine builders, by other OEMs, this asset as a service model, but still the business modeling and the business part requires more elaboration. Now, another recommendation, and we had this in several of the projects. Prophecy was one, I think. Serena was another, but also other projects. We integrated ergonomic cyber representations like augmented reality, virtual reality, and also tactile aspects, so mixed reality, simulated reality, in our demonstrators and in our use cases. There are many good technology drivers about this. For example, 5G networking, also falling prices of AR glasses and similar headsets. But I would add here COVID-19 pandemic outbreak. I mean, nobody is willing to, I don't know, for example, fly from Germany to Mexico 10 hours and then drive another 5 to a plant in the middle of nowhere to do the maintenance, right? Now with the condition-based maintenance approach and with augmented reality, you can, and with the tactile internet, you can really reduce the physical activity. You can obviate a lot of travels. So I think that was a really important use case during COVID times, which is here to stay. And similarly, you've got to empower the workers based on AR devices, also sometimes mobile devices. So I would say remote first and mobile first maintenance, or remote maintenance and augmented reality in the context of predictive maintenance and condition-based maintenance are going to be important topics for research and development, but also for innovation policies in the years to come. Now, adding a little bit more autonomy. So we heard already about this in previous presentations. So I think it was apparent that recent advances in digital technology, but also the cultural shift that Industry 4.0 is bringing in the plants, will sooner or later lead us to more intelligent and to more autonomous maintenance. So simple examples might be, for example, using smart drones for asset inspections. They are safer, you can collect more richer and more focused information, but also other forms of AI and human-robot collaboration like cobots. So we can imagine a lot of maintenance tasks where a robot is playing a role and is accelerating the process. So we are going to see more smarter and more autonomous forms of maintenance. These are driven by the knowledge extraction that you can get, by analyzing your data, because this is what will tell you when and how you're going to use the cobot. Now, training is always an important theme, and lifelong learning. So I think it's clear that we need a cultural shift in the plants, especially for maintenance workers, enterprise maintenance, predictive maintenance. These incur some change in the role of the maintenance worker. I mean, in the way you do inspections, in the way you schedule maintenance, in the way you actually fix things, and the supportive information you have for this, call it AR glasses or dashboards or cobots and so on. So it's clear that we need a certain degree of focus on upskilling and reskilling and relevant programs for workers in the factories. Now, I will end up where I did started. So indeed, maintenance is a critical element of the twin transition. So I think that now that some of us might be, looking or preparing or examining the twin transition work programs, and maybe there you won't find, some pure predictive maintenance call or predictive maintenance call text, but all over the twin transition work program, you will see that maintenance is a very important part. So when you talk about zero defect manufacturing, 0x manufacturing, or quality management, effectively you are targeting the combination of a series of interventions which span different areas, and maintenance is one of them. So maintenance, logistics, process control, and so on. And as presented in one of the previous presentations, there are indeed maintenance solutions at many different scales. So you can do things at very short time scales, for example, real time, or semi-real time, or you can collect a lot of data points to emphasize accuracy when you predict your remaining useful life. So, and of course, you can do certainly combinations of the two. So this means that you've got a lot of a very rich spectrum of interventions and of systems that are coming from predictive maintenance to support the twin transition, to support quality management, to support decarbonation of the economy and reduction of waste, and so on. So although we don't explicitly spell this out in the white paper because our focus is maintenance, I think it should be clear to everybody that one of the future directions is how do I optimally combine predictive maintenance and condition-based maintenance insights with other interventions, as I said, in areas like logistics, process control.
Presentations we have been showing today. Thanks a lot, John, for that. You gave us also so many other perspectives that may help us to think how things can move forward. I think it has been quite interesting, very interesting session. We had the chance to discuss about so many topics, technological topics, and also to hear the industrial point of view. Always the technology has been discussed in this cluster with the perspective of how the industry sees that, always considering the limitations in skills, in data acquisition, and so many other challenges we faced. The outdriver has been, as also John said, that predictive maintenance has been the main driver, but there are so many other areas that are related to that, like this condition monitoring, lifetime extension, and many other aspects. So I think that we are going on our way, and the community stays together and we keep going. In terms of 4C, there will be additional work. For now, the projects on predictive maintenance finished. We released a white paper, and that concludes the first cycle. Our website has been shared over the event, and newer announcements and newer work and outcomes will be shared on the website. The group will continue with involving more projects, and if people see themselves positioned into the context of this work, feel free to get in touch with us. I hope our contacts have been clear over the event. So I think we keep going, and we wish to find ways to be helpful towards the European industry. I think in the interest of time, maybe we covered the time that we have allocated, and the speakers took time that explained many of the aspects that one might question. Unless there are additional questions arriving, I think we are okay from our side. We covered the public event of this cluster, and since there is no additional feedback, I think we can conclude the event. Once again, I have to thank all the participants, the project coordinators for putting the chapters together, and also summarizing all the input received. Also for engaging the industry in their projects and trying to summarize what has been done. Once again, also to thank Digital Factory Alliance for giving us the floor today. And with that, I think we can conclude the event. I don't know if anyone else would like to raise something at this point. I hope I summarized our common understanding. And I guess we are good. Carmen, I think the word goes back to you, that you opened the event. And then we can conclude it.
Thanks a lot, Sotiris, and thanks a lot to all the speakers for this very interesting event, where we have listened about a lot of the insight in predictive maintenance. So the last thing is to remind you the event, the Digital Tech Talk that we have on Tuesday, organized by the Zero Defect manufacturing clusters. Thank you to all the attendants, and I hope to see you again on Tuesday. Thank you. Bye.
Thank you too. See you. Bye-bye.
Bye-bye. Bye. Thank you, Sotiris.
Thank you very much. Goodbye.
Thank you all.
Thank you. Bye-bye.
Thank you all. Bye-bye.